Alright everyone, it's Mr. Reedy back with yet another video. Today we're going to be talking about 6.4, which is on heat capacity and calorimetry. So, as we discussed in 6.3, heat will transfer from hotter substances to colder ones, right? So heat is just the flow of energy caused by a temperature difference. The way that we calculate heat is we can use this formula. Q equals mc sub s delta T, where Q is your heat, M is the mass, C sub S is the specific heat capacity of the substance, and then delta T is your final temperature minus your initial temperature, i.e. the change in temperature. And that's how we can find heat. So we can use this formula that's highlighted in blue here to actually calculate heat for whether it's a physical process or a chemical one. Okay. Now, the specific heat capacity is the amount of heat that's required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Units are going to be in joules per gram degree Celsius. And then we can also have molar heat capacity, which is the amount of heat required to raise the temperature by 1 mole of that substance by 1 degree Celsius. Okay, so guys, you'll notice here that our units for temperature are back in Celsius. Usually in thermal chemistry, those are the units we're going to stick with, is degrees Celsius. I know for almost everything else, we go to Kelvin. Thermal chemistry, we can keep it in Celsius. Just keep that in mind. The broader point would be to always make sure you know what your units are, because units will dictate what conversions you do, right? As we've talked about many times before. Now, because specific heat capacity and molar heat capacity are both intensive properties, which means, right, that it depends on the kind of substance or the type of matter that's being heated, not the amount. Okay, so in other words, if I have a water bottle, right, so probably a half a liter of water, okay, and I were to compare this to 10,000 gallons of water, a trillion gallons of water, because that substance is in fact water, it will always have the heat capacity of 4.18 joules per gram degree Celsius, because that's water's specific heat capacity. Since that's the case, we can use specific heat like we use boiling point, like we use density as a property to identify the identity of an unknown substance. Okay, so to really illustrate this point here, in table 6.4, we have the specific heat capacity of common substances. With the exception of lead and gold, you'll notice that every value in that table has a different heat capacity, whether we're talking about copper, 0.385, whether we're talking about water, 4.18, whether we're talking about granite, 0.79. All of these values are in fact different, right? And it's the same thing would be true, is that substances have different boiling points. So boiling point is often a property used to identify the identity of the substance, as is density. Again, these types of properties depend on the kind of matter, not the amount of it. Okay, so calorimetry is the measurement of thermal energy exchange between the reaction, as defined as the system. So the reaction itself, we'll call it, that's the system, by observing the temperature of the surroundings. Okay, now calorimetry also isolates the system through insulation. So what's insulation? This would be like a Yeti or a Hydro Flask. Those are insulated by a vacuum that trapped air in it. So theoretically speaking, you could use a Yeti or a Hydro Flask as a calorimeter, okay, because it has insulation. You could also use something as simple as a styrofoam cup, okay, that is also insulated. You could also use a cooler theoretically, okay. All those things provide insulation. Now, because of that insulation, if we go back to the first law of thermodynamics, which states that energy can't be created or destroyed. It can only be changed. Well, when we're in an isolated system, that means the heat being gained, the heat can't be gained or lost to the surroundings, right? It's only transferred at that point. So, therefore, we can measure the change in temperature and then thereby calculate how much heat was being transferred. So, there are two types of calorimeters that we're going to discuss. The first one is called bomb calorimetry, which occurs at a constant volume, and it measures the change of internal energy, delta E, or in our case, which is going to be far more common, is to measure the heat of combustion for a chemical reaction. And now, the formula for this is Q equals negative capital C times delta T. Now, guys, for this one here, okay, capital C is the heat capacity of the actual calorimeter, okay? So it's the entirety of the calorimeter there, okay? So it would be like the entire vessel here. That's what capital C represents, is the entirety of the heat capacity of that entire vessel. That's capital C. Now, what we'll do in class is use coffee cup calorimetry on a future lab, which occurs at constant pressure, and this measures the change in enthalpy for a reaction, and you ultimately use Q equals MC delta T to calculate that heat exchange, okay? So Q equals MC delta T is used to calculate the heat transfer in coffee cup calorimetry. In order to calculate the heat transfer in bomb calorimetry, we use Q equals capital negative C times delta T, okay? So those are our two types of calorimeters. Some useful unit conversions that you should just write down are listed on the slide. So take a moment and pause this. The one thing I just want you to take away, guys, is that our food labels are actually a bit misleading, as of 1 capital C calorie is 1,000 lowercase c calories. And well, what does that really mean in terms of chemistry? If we were to look at the actual metric system units, as well, 1,000 lowercase calories is a kilocalorie. So really, our food labels should be labeled in kilocalories, not capital C calories, but nonetheless, we're in the US. Okay, so we're going to go into greater depth into heating curves in the next video, but to introduce it is, if you guys take a look, whenever we want to talk about the rising parts of a curve, or in the future we'll see the falling parts of curves as well. So in other words, whenever the substance is just gaining temperature, right, over time, so whenever our substance is just gaining temperature, we can calculate the amount of heat required to do that by using our equation here, Q equals MC delta T. Again, we're going to talk about this in greater depth in the next video, so I'm not going to harp on it. I'm just introducing this idea that the rising points of heating curves, we can use Q equals MC delta T to calculate how much heat is needed to raise the temperature by 10, 15, 20 degrees of that substance. Okay, let's begin our example problem. And it says, let's begin our example problem here. It says a 1.55 gram sample of propane C3H8 was burned in a bomb calorimeter whose total heat capacity is 12.3 kilojoules per degree Celsius. The temperature of the calorimeter plus its constants increased from 21.36 degrees Celsius to 27.69 degrees Celsius. What is the heat of combustion per gram of propane? Okay, so guys, like in any problem in AP Chem, right, the first thing we want to do is outline what we're looking for, which is we're looking for the heat of combustion, which we represent as delta H COMB. So that means the heat of combustion, okay? And the way that we need to get the heat of combustion is we need to find the heat, Q, being transferred in this chemical reaction, divide it by, in this case, it wants us to do per gram. So we need the amount of grams, and we need to find Q. Okay, so that's how we get the heat of combustion. Now, we also want to go through and identify what was given to us. So we were given the mass, which is 1.55 grams of methane. Okay, and then we're also given the heat capacity, which is in this case the heat capacity of the calorimeter. So we have capital C, and that is 12.3 kilojoules per degree Celsius. We were given the initial temperature, TI, which is going to be 21.36 degrees Celsius. And then we were given TF, which is 27.69 degrees Celsius. Okay. So since this is occurring in a bomb calorimetry, in order for us to calculate the heat exchange, what we need to use is Q is equal to the negative capital C times the change in temperature. So negative C would, of course, be the specific heat of the calorimeter. So we'll plug in our values. Okay, and then our heat being transferred is going to be negative. The heat being transferred is going to be negative 77.6 kilojoules. Okay, now guys, I want you to know that that negative sign means that the heat that this reaction is exothermic, so heat was given off, and it's also evident here that heat's being given off because of the value, right, of the temperature increased, right? So the surroundings increase, so the temperature then is going to be negative 77.6 kilojoules. So this is going to be the value we're going to plug in over here, okay? So negative 77, we'll plug that in up top. And then we already had our mass, guys. It was over here. They gave us the mass. So that 1.55 grams goes here. And the one thing that we do have to make sure we're realizing here is that this was the heat transfer to the surroundings, right? So it's an exothermic reaction, we just realized that, but this is the heat transferred to the surroundings, okay? Right? And so, again, that negative sign is just indicating that this reaction is exothermic. Now, what we're going to do is just divide this out, and we're going to get the heat of combustion is equal to 50.2 kilojoules per gram. And don't forget the negative sign. Now, in terms of this being our final answer, it indeed is. The one thing that I do want to talk about that you could see that is just one extra step is sometimes they might ask you the heat of combustion per mole of that substance. And if you were, if it were to ask you to find per mole, well, you would take the grams they give you, convert that to moles, and instead of dividing Q by grams, you divide Q by moles. So it's just one extra step, one little conversion. You would need to go grams to moles first, and then again take your Q, divide by the moles. So again, sometimes you might run into that where they might make you go one extra step. But that's that. Let's continue on now. And we've got this problem, which says 50 milliliters of 0.5 molar HCl was added to 50 mils of 0.5 molar NaOH. The initial temperature of the solution is 19.8 degrees Celsius. The reaction occurred as stated below. So HCl reacted with NaOH to form salt plus water. Hopefully you remember that this is an acid-base neutralization reaction. And when that happened, the temperature increased to 26.3 degrees Celsius. I want you guys to try to calculate the heat gained by the mixture, and then what is the heat capacity per mole. Now, guys, there is one thing I have to state before you start to calculate this. Because both HCl and NaOH are dissolved in water, right? They're both dissolved in water as they are aqueous solutions. We need to use the specific heat of water, okay, which is going to be 4.18 joules per gram degree Celsius. And then the other thing I need to fill you in on is the fact that if you guys look at the 50 mils in both parts here, well, when you add the solution together, your mass is really going to be 100 mils of water, right? Because, again, these things are dissolved in the water, okay? And thankfully, water has that unique ratio where 1 gram is equal to 1 mil of itself. So if you have 100 mils of water, you actually have 100 grams of water. And with those ideas out on the slide now, you should be able to go ahead and do this on your own. So take a moment and try to get 1 and 2, and I'll be back with the answer so you can check. Okay, and I hope you got that the heat that is being gained by the mixture is positive 2,717 joules. But in order to get part 2, you do have to flip the sign, because the gain by the mixture, that's the surroundings. So the Q system is equal to negative Q surroundings, as we saw during 6.3. So therefore, we plug in for the system for Q is negative 2,717 joules. We divide by 0.025 moles. How did I get moles of NaOH? Well, we take 50 milliliters. We divide that by 1,000, so we have 0.5 liters. Multiply that by the molarity, and we're in moles. So that's where that 0.025 comes from. We divide them out, and you'll get negative 110,000 joules per mole, or to keep things nice and simple, negative 110 kilojoules per mole. And that's the end of the video today, guys. If you have any questions, please shoot me an email.